Hello and welcome to another video. In this video, we're going to be doing probably our hardest problem yet in the Blind 75, and it's going to be word search 2. So in this problem, you're given an n by n board of characters and a list of strings words, and you want to return all words on the board. And each board must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring the same letter and may not be used more than once. So essentially, we're given some board of letters, and we're trying to find all of these words. So oath, for example, does exist, and you go here. And you can't use the same letter multiple times, so you can't be like O, A, O, A, O, A, O, right? So you can only use one letter once in each word. Then we don't have P because we don't have the letter P. Then for each, we have that right here. And rain, we do not have. So you would just return the words you did found. And in the second example, it looks like there aren't any of these because to get A, B, C, B, there's only A, B, and then you can't go diagonally. So this is going to be a combination of word search 1 and our trie data structure, right? So word search 1 was the same thing, but we're asked to find one word. And if you recall, what we did there was we had a backtrack function. So we just started at every cell, and we just had a backtrack function that would try to visit every single cell and update the letter. So for example, if we're looking for the word oath, let's say, we would start at every cell, we would look for the first character, and then if we find it, we would try to go everywhere else and look for the A and so on. And then if we couldn't find it, then we would go back and backtrack, essentially. You're basically doing a backtrack function. And so you need to also have a visited set to make sure that you don't like repeat your work, so you can't go back and forth, right? So you don't want to go from like O to A to O to A to O to A, right? So you need a visited set to do that. So essentially, we're going to have a backtrack function. So backtrack, just like in word search 1, and if you don't remember that one, you can watch that video. And we're going to implement a trie, like we did in the last like 2 or 3 videos, to store all of these words. So now instead of going letter by letter through the word we want, we're going to be going node by node through our trie. And if you think about it, essentially we're just going to be going node by node through our trie. And every time we find a word, we basically have to go and write it in our result. And so we're going to make our trie a little bit differently this time. Instead of actually so our trie originally had like a children object, right? It had a children, and it had a word boolean. Well, now instead of a word boolean, we're going to make it a little bit more convenient. Instead of the word boolean, we're just going to have a word that's going to equal a string or a null. So if the trie is the end of a word, we're going to have that word, and then if the trie is null, that means it's not a word, right? Similar to the boolean, except now the word will actually contain the word. And we're going to be doing the same backtrack thing. But now the only difference is we're just going to be doing we're just going to be going through a trie instead of a word. So everything else is going to be literally the same. We're just going to be going in every single direction that we can in a backtrack function. And then we're going to keep passing new tries in instead of the new word. So everything else is literally the same. We're going to go through every single index, write a backtrack function, and do that. So it's literally, if you know how to do word search 1, and you know how to make a trie, it's basically a combination of those. It's just going to be like a lot of code. But everything else is literally all the same. So for example, let's just like really quickly go through this, let's say. So let's say we build a trie of oath, P, eat, and rain. So what would that look like, right? So we're going to have our root trie. We're going to build oath first. So let's have O, A, T, H, and then P is going to start with a different letter, so P, E, A, it's going to be like this, and then eat is going to start with a different letter, so E, A, T, and rain is going to start with a different letter, so it's just going to be like this, A, I, and N. And all of these are going to symbolize like the end of a word, so all of these tries will actually have the word they represent. So like this trie will have eat, this trie will have oath, this trie will have P, and so on. So essentially, let's just kind of see what it's going to look like for this oath example, and then like just starting at this node, and then we'll go and do that from there. Well, we're going to be doing the same exact thing like all the way down. So essentially what's going to happen is here we have an O. So we're going to start the root node of the trie. And essentially we have an O. So we're just going to check like, is there an O? And yes, there is, right? So then we're going to traverse down to the next trie. And then we're going to go in every single direction from here. So we can't go here. We can't go here. We're going to mark this O as visited. And we are going to go to like this A, let's say. So we're going to be at this A and we're going to check, is there an A? Yes, there is. So we're going to traverse down here. And we're going to mark this as visited. And we're going to try to go in every direction. So we can't go here. We can't go here. Let's try to go right again, for example. Then we're going to check, is there an A from this trie? No, there's not. So then we're going to go back. Right? We're going to go back. And we're going to mark this as visited. And so then we'll go back. And we'll actually go... Actually, we're not going to mark this A as visited. We're just going to go back. And then we're going to go to this T next. So we're going to check, can we go to this T? Yes, we can. And then from this T, once that's visited, then we can go left, let's say. So if we go left, there is no E. So we're going to go back. We're going to go right. Is there an A? No. And then we're going to finally go down and hit this H. And then once we're at this H, we're going to have a completed word. But you can't really stop once you have a completed word because you might have like multiple words, right? You might have like rain, and then you might have like a rains or rainy and so on. So you literally just keep going until you run out of places to go to with your visited set, and until you basically run out of your trie, right? But that's essentially what we're doing. We're traversing our trie. We're going to pass in the new trie that we go to every single time, and then that's how we're going to build up all our words, and we're going to start at every single point, and at every single point, so the other thing we have to do is once we use our letter and come back, in the backtrack part, we're gonna clean out the visited set. So essentially, when we go to a new letter, like let's say we come here and we use this letter, we'll put it in the visited set, and then once we're done with the letter, we will take it out of the visited set. And instead of a visited set, this time I'll just use a 2D array instead of a visited set. So you could do one or the other. You could have a visited, or you could have a visited set, or you could have a visited array or whatever. Same thing for hash map. For these kinds of problems, you can have a hash map that's an array or an object. Either one's fine. Okay, so now let's get into the code, and it's going to be a ton of code. So I have this trie written up for us, and it's basically the same as the other trie. So if we take a look really quick, it has a children, has a word. Now instead of a Boolean, we just have a string. And then it's going to have an insert function that's literally the same as the other ones we've been doing, where we make a root trie, we go through every single character, we add all of the characters in, and then finally, the only difference is once we get to the very end, once we went through the whole word, instead of setting a Boolean, we're going to set an actual string, right? So whatever trie we're at the end, we're going to say no.word equals the word. That way, when we traverse a trie, anytime we have a word, we don't want a Boolean, we want to know what actual word is it. So this is going to make it convenient, or more convenient, to have our stuff this way. And so now let's actually code up our find words function and figure out like what we need and stuff. So in our find words, we need a few things, right? We need our actual result. So let's have that first. So we can have result, and it's going to be an array of string. And you can write this in a bunch of ways. This is just one way in TypeScript. So this is what we want. This is the same as this also. Like if you wanted to write it like that, like this is also fine, but we'll just do it this way for now. And so we're going to have the rows and the columns just to get the dimensions of our actual grid. So rows equals board length. And we're going to have the columns equals board 0 length, as always. Then we're going to have our directions, because we're going to want to try to go in every direction, just like all my other problems. So we're going to have 1, 0. We're going to have 0, 1. Negative 1, 0. 0, negative 1. So there we go. We have all our directions, and now we're going to have a visited array instead of a set, just to show you something different. So the way to make a 2D array that's pretty convenient is what you can say is you can say visited equals new array, and then you can set like one dimension of it. So let's say we have rows here. then what you could use, you could fill it with whatever you want. And then to make the 2D part of it, you just map the other dimension. So you say you fill it with amount of rows, and then you map a function that will, in every single location, will make another new array of length columns. And then that's the actual thing that you want to fill with whatever you want. So in our case, we're just going to fill it with booleans. So false will be not visited and true will be visited. And so whatever index we get to, we can just plug that into our visited array. And if it's true, it's visited, and false, it's not. Now we're going to make a root. So we're going to say const root equals new try. So this is going to be our root try. And now we're going to actually go through all of our words and insert them. So in my try, I actually wrote an insert function, just like, I think I've wrote like 4 or 5 tries by now. So we're going to call this insert function just to make it more convenient. So we can say for let word of words, let's actually insert it. So root insert word. Okay. So now we can actually write our main backtrack function, which is going to be like most of our code. Okay. So in our backtrack function, we're going to have a couple things, right? We need a row, which is going to be a number. We need a column, which is going to be a number. And we need the current node we're on in the try. And it's going to return a void. So first thing we're going to check is if we're actually out of bounds or visited. So if we're out of bounds or visited, we don't want to like do anything. So if row is less than 0, or this is all the same as like all the other stuff that I've written before. If call is less than 0, or there we go. So if call is greater or equal to calls, or it's visited already, we don't want to like repeat our letter or take anything out of bounds. So if any one of these is true, let's just return straight away. We don't need to do anything there. So the other thing we need to do now is we need to actually check, is our try that we currently have, like, is the try we're currently in, does it have this letter? Because if it doesn't have this letter, then we can't traverse to this letter, and that's also useless. So if not, and this is, like I said, you can do this a bunch of different ways, but I'm going to do the has zone that I've been doing. So no.children. So essentially, if this letter is not in the children of the current try we're in, then we can also return, just return. Okay. Need this, and yeah, okay, that's fine. Okay, so now that we know that this is valid, right? The index is valid, and our current try actually has this letter. Now we need to actually mark it as visited. So we're going to mark it as visited. It's a visited row column. We're going to say it's true, and then at the end of our backtrack, we will update it to not visited, because we still do want that to be part of a word that just can't be like used multiple times while we're using it now. So then we essentially want to get a new node, right? So we have some node. Now we want to go to the next node in the try. So we will update our node. So node equals node.children board row call. So essentially we are just traversing like to the next try. And now we actually have to check, does this try finish a word? So if whatever word we traverse down, or whatever try we traverse down into, if that's actually the end of a word, we have to check for that. So if node.word, remember it's a string or null. So if this is true, it's going to be a string. So if it's true, we're just going to push this to the result. So res.push, node.word. And the thing is also what we want to do is we don't want to like get the same word multiple times, right? So, but we still want to like be able to get to this try. So what we're going to do is once we use this word, we don't want to actually get to the same point again. So once we use this word, we're actually going to set the word to null, meaning like we don't want to get the same output again, because we might get to this try again, right? Like let's say, for example, our try was just the letter A, and then we can try a bunch of A's, right? We can try like apple, whatever, right? We can keep getting to that A. There can be multiple A's in the matrix. And if A is one of the words that we're looking for, and this is essentially sure we're not using the same word multiple times, or you could use a set here, but setting it null also works. Okay, so now we have to go in every single direction. So what we're going to do is we're actually going to destructure the directions. So we're going to say for row column of directions. So essentially we have to go in every single direction, right? We have to go up, down, left, right. So we can say backtrack row plus R and call plus C and the current node we're at. And I believe that's actually it for this function. So just to like repeat what we're doing, essentially for our backtrack function, if we're out of bounds, we can return. If we can't traverse into the trie, meaning if the current letter is not in the trie, we can return. We want to set it to visited. And then we want to actually go to like the next node so that we can pass it into our backtrack function. And we also want to check, is that node actually a word? And if that node is a word, we want to actually push it into the result. And we want to set the word to null so we're not like pushing the same word multiple times. So we did actually forget one thing. We forgot to set this visited to false. Because for this backtrack, like for now, we want to set it to true. In our current node, we might be done with it, but we're definitely it's definitely possible to visit the same letter a bunch of times. That's why I think when you look at the constraints for these are really small because this is going to be a super inefficient function and there's like nothing you can do about that. So now that we have our backtrack function, now essentially we just need to loop through every single starting index and call it. So if a row equals 0, then this was just like the same thing we did in the original word search. So basically the only difference is now instead of a word, you use a trie. And all the other stuff is all the same for one word versus a bunch of words. So for let call equals 0, calls less than calls, call plus plus. We just call backtrack on row, column, and our root trie that we made. And I think that is it. So let's hope like I said, this is like one of our chunkiest things of code, so we'll see how this goes. Okay, I probably do want to actually get out of this now so I can see our errors. Let's take a look. Function whose type is neither undefined, void, or something must define. Oh, I see. Oh, did we not return our, we probably just didn't return the result. Yeah, so it looks like, oh, and we also forgot to actually, so we got out of the backtrack, but we never actually returned the result here as well. So let's see where this actually ends. So this closes here. Yeah. So we need to return the result all the way at the bottom here. So return the result. Let's see if I called it res. Hopefully I did. Yeah. Okay, let's try that. Okay, so that did work. But yeah, this one's definitely quite big, and like I said, I would first focus on doing word search 1, really know that you understand that, and then do these try questions that I had in these previous, like implement a try, design a word search, all these things. And once you're good with both, you're essentially just combining them into one problem. So it's definitely a chunky problem, but as you can see, we have a reasonably efficient solution. It's going to be pretty tricky to find. This is going to be one of the trickier problems to find the time and space, but let's see what happens essentially. So first, we have to put every word into the try, right? So whatever that is, that's just going to be like the total amount of characters in all of the words combined. Let's call that O of characters, right? Worst case scenario, we'd have to make a new try for each of these. So that's going to be that part. Now for the actual backtrack part, essentially for every single index, so that's rows times columns already, right? We have to start at every single index. And how far can we backtrack essentially into all of these? Like how many places do we have to check? Well, at every place we can check 4 different locations, right? So it's like 4 to the whatever like the longest letter is or the longest word is in this like actual thing, because the longest you'll ever go is like the length of a word, right? So this would be like 4 to the length of the longest word, so like some kind of word length situation where it would be the length of the longest word. So like this is, if we take a look at the constraints here, so it looks like the length of a word is 10 characters. So this is 4 to the 10th. And then rows and columns is only 12 and 12. So that's why these constraints are really small, because this gets really inefficient really fast, essentially. Like at every single place you're backtracking, you have to check 4 directions, right? And so this gets like really inefficient really fast. And yeah, the farthest you can ever go is the length of the longest word in your try, basically, right? Because you can, like, you're just gonna be out of bounds. So this is gonna be like longest word length or something in your try, which is like roughly 10 or something. Okay, now let's think about the space. And this could be wrong, but I think this seems pretty reasonable to me. So definitely, if someone has something else, they can let me know. So for the space, so we are making like all of these tries again, right? So that's going to be the length of all the characters combined. So it's going to be, and I guess this is also plus. Yeah, length, and then technically, I mean this, yeah, I think you do have to add them because let's say you have a bunch of words that you're adding, but then like the longest, you know, the row, like your matrix is only like 1 by 1 or something. Then you do have to add them, I believe. Okay, so the number of tries is the number of characters. Now let's kind of look at all the other stuff. So we have the directions, which is basically negligible. We have a result, which is an array of all the words possible, which is going to be, once again, like worst case scenario, every single word, which is the number of characters total in all of your words combined. Then we have this visited set, which is m by n. And then we also have the recursive call stack, right? So the visited set is going to be rows times columns, or the visited array is going to be rows times columns. And then the recursive call stack is going to be, like, you can have a bunch of tries saved, but that's also going to be the length of the longest word. I mean, I guess technically you can add that if you wanted to. I think this is gonna supersede that because like the longest word is going to be stored as a bunch of tries, so the longest word will be in this already, technically. So I think this is just like, yeah, so this chars is all the characters in every word combined. But yeah, I think that's going to be it for this one. Definitely hefty amount of code, and I would definitely encourage you to try the smaller ones before this one. But yeah, I think this is going to be, it's not like super tricky, it's just a lot of code and combining a bunch of things into one. So yeah, it's going to be all for this video though, and if you liked it, please like it, and please subscribe to the channel, and I'll see you in the next one. Thanks for watching.